This segment we're going to talk about the cascade refrigeration cycle. So from state 1 to state 2, you have an ideally isentropic compression process, then a constant pressure heat rejection process, then an isenthalpic throttling process, and a constant pressure heat addition process within your evaporator from that refrigerated space. So what you see is this looks exactly like a simple vapor compression refrigeration cycle, and it is. The difference comes when we add another vapor compression refrigeration cycle on top of that, and that's why it's called a cascade refrigeration cycle. You got more than one vapor compression refrigeration cycle working together. So I've got cycle A, and then on top of it, I've got cycle B. So it's the exact same thing. Simple ideally isentropic compression process, constant pressure heat rejection process to your high temperature reservoir, isenthalpic throttling, and then you've got a constant pressure heat addition process, and that heat added to that cycle on the very top is coming from the bottom cycle. So you've got cycle A and you've got cycle B. And in cycle A, because this is completely separate from cycle B, you can have two different refrigerants. So you might have refrigerant A and it's going with some mass flow rate A, M.A, and refrigerant B, you can have a different refrigerant. So why would you have a different refrigerant? Well, maybe you want to take advantage of the saturation pressures at the desired temperatures of your refrigerant within your cycle. So what I mean is this. In your evaporator, which is at the very, very bottom, the refrigerant that's passing through there is passing through at a constant pressure. And it's also going through a constant pressure phase change. So the temperature is constant as well. Now, when you design your refrigeration cycle, you want that temperature that's going through that bottom heat exchanger, that evaporator, you want it to be colder than the refrigerated space so that heat flows appropriately. And when the temperature that's the temperature of your refrigerant that's going through that evaporator, you need the saturation pressure at that temperature not to be too low. If it's below atmospheric pressure, it could pull air into your system, and you don't want any air coming into your system. And you can make a similar case for the very top heat exchanger, the condenser. You don't want the pressure to be too high. You don't want the saturation pressure at whatever temperature that you need to be at in the condenser. You don't want it to be too high because that increases the cost of your material. So by choosing two different refrigerants, you can kind of tweak those the pressure in your condenser and your evaporator to reasonable pressures. All right. So what if we wanted to accomplish what we just did with that cascade cycle with just one vapor compression refrigeration cycle? But so I'm still going between the low pressure and the very high pressure in that cascade refrigeration cycle. So it would look like this. I would start off on that saturated vapor line as I entered the compressor, then I would compress isentropically all the way up to that top pressure. And then the rest of it would kind of look the same. Constant pressure heat addition or heat rejection process. Then you got an irreversible isenthalpic throttling process and a constant pressure heat addition process. So you can sort of see in the background where we came from, what the TS diagram for that cascade refrigeration cycle looked like. And this is what it would look like if we tried to do it with one cycle. So let's go back to that cascade cycle. What we see is that you are pulling heat out of that refrigerated space and adding the heat to your cycle in between states 4 and 1. And so if I compare these two scenarios, I can see that if I use a cascade refrigeration cycle, I'm allowed to pull out even more heat from that refrigerated space. So I increase my refrigeration capacity by using a cascade refrigeration cycle. And the other thing that I do is I decrease the amount of work that is required for this cycle. So by dividing up that compression process, I decrease the total amount of work that's required to reach that high pressure in between states 6 and 7 in that cascade refrigeration cycle. And the result is an increase in the coefficient of performance. Now, when you analyze this, you've just got two simple vapor compression refrigeration cycles. So if you know how to analyze a simple vapor compression refrigeration cycle, you know how to analyze this guy. All the components are the same. The only thing that might give you pause is that middle heat exchanger, and you still know how to analyze this. So you've got an open system, you apply your first law, and of course, the only heat that you want to be exchanged is in between those two loops. So the entire heat exchanger unit is going to be insulated. So once you get rid of your Q dots, your W dots, you assume it's steady state, you get rid of those kinetic and potential energy changes, all you're left with is M dots and the H's. And so coming in, I've got things coming in at 2 and 8 and things leaving at 5 and 3. And what I can do is I can kind of manipulate this just to relate my mass flow rates and the enthalpies. All right, well, I hope that was helpful. Thank you very much for watching.